So thank you very much for inviting me. It's been a great workshop. I hope I get invited at KIPAC 22. And maybe we'll be able to say something more than the speculative thing that I'm going to talk to you about now. But the idea of this talk really is the following, that I think honestly we're 90% of the community is working on, in cosmology is working on the assumption that the dark energy is lambda. And I think that is perfectly the right thing to be doing. Because honestly speaking, we're only going to seriously consider this sort of models if we find that something doesn't match and we cannot really explain it. But the question then becomes, if we find that something doesn't quite work, W doesn't seem to be quite -1, for example, that's the sort of most basic property of a dark energy that wouldn't be lambda. How do you actually say what it is, and how do you understand how do you actually explain what you're seeing? Because the issue is that one thing is a measurement and discovery that something's not right, that's not lambda. Another thing is actually being able to say, oh, in this framework, this is how I would actually explain it. And the real problem we have right now is that we don't have a compelling model, honestly speaking, for a dark energy that would be different. We have ideas for what kind of phenology we might be able to see, but we don't really have a good model. So we don't really have a framework really to think about it. So I'm going to give you some ideas about how to get from we've seen something that's not lambda to maybe some sort of statement about the properties of what it is that we've seen. So in general, let's see what the theory space is first, and then try to see what might be possible to see, what we should be expecting to be seeing, what we should be expecting to measure. So I make the first point following Lenny's talk, is that whatever, if we measure something that is not lambda, we have a problem at hand anyway, because whatever model we come up with, we have to tune lambda away. And I think Lenny explained why that is the case. And I think that's kind of actually got a bit more complicated than it was maybe, because it seems now that after Planck, inflation really is the very standard run-of-the-mill plain vanilla inflation with a scalar field and effectively a potential that is a vacuum energy. So it's clear the vacuum energy must gravitate, otherwise this mechanism wouldn't work. So it cannot just be the case that one of the solutions could be that vacuum energy is not doesn't gravitate, but the fact that the inflation mechanism is to work, that basically excludes that. And the problem that, on the point of view when you think about it from dark energy now, is that the models that we've been playing around with for the past 15 years, let's say, quintessence, modifications of gravity like Hova, that sort of thing, basically all have been put in this part of theory space now where they're more or less vacuum energy plus something on top. So they're really slightly more complicated forms of a cosmological constant, effectively. So the sort of typical things that people look at are kind of slow roll models. So you basically have some additional degree of freedom, a scalar field, I'm going to call it phi over here, which rolls. And it needs to roll slowly, otherwise the acceleration wouldn't, you wouldn't be seeing the acceleration. So typically what you have is that your kinetic energy, sorry, how do I actually, where's the top one? Yeah, so the kinetic energy has to be much less than the potential energy. So you can just do some expansion, and you basically get that there's a sort of vacuum energy, which is basically cosmological constant plus something on top. And you've traded this problem of just having a cosmological constant problem here, which was this small vacuum energy, to also another one, which is now we have to have a mass that, if it's supposed to do anything that's interesting, this mass is supposed to be reasonably small. So you now have a hierarchy problem on top of a cosmological constant problem. So this is, and I basically will agree with Lenny that sort of, I'm not particularly enamored with quintessence models because they sort of complicate matters rather than making them, giving real alternative. It may be the case that this is what we'll see, but sort of from a theoretical level, sort of, I'm not sure whether it's really very compelling. Another idea was this idea of modifying gravity, which sort of ended up looking the following way. You say that there are two metrics. There's a metric where gravity is Einstein gravity, sort of. The gravity is normal, effectively, in some metric. There's some degree of freedom, which is some scalar, which is coupled to this metric. And then matter only knows about the combination of the two. So matter somehow propagates in a different metric to the Einstein one. And the nice idea there was that the Hubble parameter that you would observe, thinking that things move on geodesics, would in fact consist of two things: the normal Hubble parameter plus something to do with the motion of the scalar field. So now, if you had the scalar field that was moving very quickly, then you would find that what's called the Jordan frame, the Hubble parameter that you'd think you'd be observing, in fact, would be doing something else than you'd expect. For example, it would be accelerating. But the key thing there was that really you have to have a fast-rolling scalar field of some sort in order to be able to have a big difference between these two frames. And the problem is that all of these models produce fifth forces. So there's an additional attractive force, which all matter seems to follow, which all matter is fields. And we have very good, very tight tests in the solar system about it, on these forces. So if you take that into account, what you find is that there's a limit on the value of the scalar field, basically. It's a sort of reasonably model independent. It needs to be a small number. So that's the scalar field itself needs to be a small number. It can't ever have evolved very far during the whole history of the universe. And if that's the case, then this phi dot can never have been very big. And therefore, you could never really have a very big difference between these two frames. And therefore, yet again, your acceleration is being done by something like cosmological constant. So this is the problem of all these sort of models. So really, you have acceleration being done by cosmological constant, and then you have an additional degree of freedom, which complicates things more. So should we just give up? Well, so this is not quite the case. So now I'm going to talk about models which are sort of less complicated, but I find actually a lot more interesting. The idea here is that you're not dealing with, a canonical scalar field. What you're dealing with is a something that has a modified kinetic term. So this x here, if you think about the cosmological background, is basically the kinetic energy of this scalar field. You can create a Lagrangian that looks like this. So, if you're thinking of x being small, this is actually, the sign is wrong here, but let me ignore it for the moment. You would basically, this is a small, with a tiny correction to this term over here. But you could imagine situations where you have a very, you allow the scalar field to be moving very quickly, to be a fast-rolling scalar field. And when you do that, you find that this is completely generic in this sort of models. You get attractors, which basically look like they have W equal to -1. So you start the model of somewhere up here. This is not a plot of the potential, by the way. There's no potential energy here. The cosmological constant here is exactly 0. That's the very important point. This is a plot of this Lagrangian, which is basically something to do with the pressure of the system. You started over here, and the system will just evolve to some minimum. And when it's at this minimum, W is exactly equal to -1. But it's not. So despite the fact that your geometry is de Sitter, in fact, you've broken Lorentz invariance here. So there's this scalar field which has a value. It's basically pointing in some direction. It's some time-like vector. In particular, it can be perturbed. So whereas a cosmological constant really is a constant everywhere, this thing looks like something that's accelerating, looking more or less like W equals to -1. But on top of that, it can have perturbations with 0 sound speed, so a bit like dark matter. This doesn't work as a dark matter model, but you see, it's a fundamentally very different object. And this basically arises from the idea that you could have large kinetic energies in very particular sort of Lagrangians. But okay, but this is me saying, you look, there's some Lagrangian, blah, blah, blah. You know, there's a sort of, we tend to, you know, people tend to write things down that are very complicated sometimes, and so sort of explain what the underlying physics may be. But actually, there's a very simple way of thinking about this, and that's that really all these Lagrangians of this type. So this is some P of X theory. This is about the same age as KIPAC, actually. This P of X theory is actually a perfect fluid. Actually, it's a perfect superfluid. Let me be very careful about this. So this is this idea that if you can identify with the gradient of the scalar field, which has to be time-like, with some velocity, then the energy tensor you can write down to all orders, right? This is not a question of, oh, my cosmological background looks like a perfect fluid. No. To all orders, you can write this down as a perfect fluid energy momentum tensor. And on top of that, there is a sort of particle number that you can identify. And then the equation of motion is really just conservation of particle number. So this thing really models relativistic hydrodynamics of a superfluid, of a mode which basically only has potential flow, does not have vorticity. And you can really write down the thermodynamic properties of this. The energy density, the pressure, the particle number, they're all just functions of one thermodynamical potential, which happens to be x. And you can think of this, you know, looking at this, what I've written down here, if you want the equation of state, actually boils down to being something like an Euler relation. So at zero temperature. So you really have a relationship between rho and p is related to the particle number that happens to be in this thing, and this root 2x, which is to think of as a thermodynamical potential, something like chemical potential, for example. So the reason, you know, you may have got lost here completely, but the point of this is that you don't necessarily have to think of a scalar field as being a fundamental degree of freedom. Oh, as Lagrangian, there's a scalar field, I really have to find this particle there. It is really, you could think about it as being an effective mode for something else completely. So I could have written down a theory of this type for a bunch of electrons sitting at zero temperature, just because of the fact that I have a cosmological background, so broken Lorentz invariance. There will have fluctuations. There'll be like phonons in this fluid of electrons, and those will be described by this Lagrangian. So you see, it's not really necessarily a fundamental degree of freedom. Some theories, not all, and it's very important. This does not depend on phi at all. This shift symmetric. Some theories can be thought of as being effective theories for a mode and something else completely. So maybe this is a way of thinking about this. Like could it be that there's just some stuff out there? There's not a scalar field, fermions if you want, neutrinos, I don't know. And they have some property like this. So thinking about this, but the point here is that this stuff happens, it's most interesting when X is large, so they're kind of fast-rolling, these fast-rolling models. So you know, so this is kind of my preferred way of thinking about it now. So I don't really know what the theory should be. But what I would like to discuss is a sort of the idea that there's just one degree of freedom. I don't know what dark energy is, but let's imagine it's just a single degree of freedom on top of just normal gravity plus dark matter, etc. And then you ask the question, what is the most general thing in the framework of thinking about Lorentz invariant theories and so on that I can write down that will satisfy this property of being a single degree of freedom? And it's something like this. So the thing I've just told you about, these sort of perfect fluids, are just this one term here. Now I can write down more complicated things, but there's only 3 classes of terms I can write down. Anything else is going to introduce extra degrees of freedom that are unstable. So this is the most general Lagrangian you can write down for a single degree of freedom now. And we have shown, for example, that if you take these two together, this model is called kinetic gravity braiding. This is, again, it's some superfluid. You can think of it as superfluid. And what this term does, it introduces it introduces something that's like an imperfect part of it, to the fluid. So in general, the energy-momentum tensors for all these three will be somehow related to the fact that the fluid is no longer perfect. Okay, so how do I think about all of this? So either I can think about, I'm going to look at a set of theories where the kinetic energy is small. So the most general theory I can write down with the kinetic energy small is exactly this, which basically is kinetic energy, potential energy, and some coupling to gravity of this sort. And depending if I pick any two of those three, I get one of these theories. So potential plus kinetic energy, I get just quintessence. If I ignore the kinetic energy and just have these two, I get F of R gravity. Or if I take X and plus the coupling, I get Brans-Dicke theory. So these are kind of well-known and studied. So the question really is, what might you see if you're in this fast rolling regime, which is more like a hydrodynamic, which has this sort of hydrodynamical picture behind it. And then the right way of thinking about it is that whatever the cosmological background is doing, so it's solving some equation of motion coming from this Lagrangian, right? But you don't know, and you know that more or less it's W is close to -1 or something like this. But it's completely arbitrary which functions here I can pick. So if I could give you a compelling model, and maybe something like this might be more compelling because everything is small, that would be like one framework which could work. But if I say, oh, well, things could be large or large too, it's quite possible. It's just hydrodynamics. It's nothing very complicated as a what the output is. But the Lagrangian itself might be complicated, but the physics isn't. I could be effectively, I'm free to pick any of these functions here. And this is this problem that we've had in dark energy for a long time. How do you decide what you should pick as your function? So my argument is that we shouldn't really be thinking like this. The way we should be thinking is that there's just some background. On any of these things, I can realize something looks like W close to -1. Okay, so there's a sort of background which evolves across these four operators in some space. And then the question is, this is the only way to tell apart any of these theories, is how do the perturbations evolve on top of this background? The idea here is basically that you can take this Lagrangian, is very complicated, and the details don't really matter. But you need to write down some action for perturbations on some background that you will measure. And this is a little bit like what people have been doing in inflation, basically saying that there's a background with a particular symmetry, it's FRW, and then on top of that I have some theory, and I would like to write down the most general thing I can write down. And what you find out, it sort of reduces. I had 4 classes of terms over here. And you should think about it as classes, right? So each of these give you new properties of physics. And these 4 classes reduce to 4 different types of terms, which give you different properties for the dark energy. And in particular, it's been proven actually that one of them, at linear order, ends up reducing itself to this 5th term here, ends up reducing itself to the 4th one here. So really, you're dealing with 3 different things. And then the background solution determines, effectively, how big these coefficients are relative to each other. So there's some operator, which is a function of scale. And this is the important thing. There's some operator, which is a function of scale, which is fixed. So this operator here, for example, it encodes Jean's length. So this is some perfect fluid, which has a Jean's length with some sound speed. And therefore, above the Jean's length will collapse, and below it will have pressure support. And there are two more classes of operators, all of which come with, and this is the very important thing, all of which come with a scale dependence that goes as k². And why is that? It's very easy to see because it's you're dealing with an FRW background, and because the symmetry is there, you can't ever mix space and time derivatives together. So your energy momentum tensor for this thing always comes with corrections that go as k². And what corrections are those? I'll get into some detail in a moment here, but if you're familiar with this stuff, they either, so you get some standard perfect fluid, you get corrections where from this K3 term, you get corrections which cause the dark energy to collapse. So effectively what happens is that there's around all the dark matter, there's dark energy also, so you think that you have more matter than you do, and therefore your effective Newton's constant seems to be larger, gravity seems to be stronger. And there's an additional one which does the same thing, but on top of that also gives you anisotropic stress, which is one of these tests of modifications of gravity. Now, this is what you got, this k-squared dependence, because I assumed I have 1 degree of freedom on FRW, which is Lorentz invariant. Now, you could imagine that you could do something else. So I could have said that I have some theory that's Lorentz violating initially. And then what you'd find is that there's a different power of k that this produces. So on some level, there's a way of excluding any sort of theory in this framework. But the only way to do that is to say, I have some scale dependence, and I'll tell you in a moment what and how. I have some scale dependence which go as k-squared, and if it's not as k-squared, then this thing is not described by Lorentz invariant, by single degree of freedom as Lorentz invariant. But for example, I might be sitting in some brain world situations, in a situation where where the corrections go as k. So how do you observe this? The idea is basically the following, is that dark energy has some perturbations. I don't know what they are. But the effect of them is very well known. You know, I have some Einstein equations where I produce a perturbation in dark energy, which contributes to my gravitational field, and then maybe I have some anisotropic stress. Now the issue is that people tend to, the way people do this, they say that I have some effective, so I have these two parameters I can write down. I compress this information for this degree of freedom into two parameters, the function of scale and time, and I parameterize them to be something simple. But actually, there is no reason to do this. Because what you can actually do is you can reconstruct from looking at the sort of tests that we'll be performing with gravity. You can reconstruct the metric in which everything's propagating. So looking at the redshift space distortions, you find that it's possible from redshift space distortions to actually reconstruct this potential psi, which is accelerating galaxies. So this is a different way of thinking about this than people normally think about it. People normally say, I can measure dark matter growth rate. This is not quite true because you're never sensitive to dark matter on its own. You're only sensitive to potentials. But here you can reconstruct this psi. And from the lensing, you can reconstruct a different combination of the two potentials in gravity. So what's possible to do is you can reconstruct as a function of z and k anisotropic stress and gamma, which is not the growth rate of dark matter, but the rate of change of the potential. You can take this requires you to take some derivatives of the data, but this can be reconstructed. So now you can use this in the following way. So this is the most general scalar field theory for a single degree of freedom you can write down. I can eliminate the scalar field. So I have basically different components of the Edgemont tensor. I can eliminate the scalar field from it completely. And I can write down an equation, which is an equation purely relating the potentials that I have measured, that are in principle possible to measure, and the velocity of the dark matter, which is also something that is possible to measure for redshift space distortions. And any scalar field theory will have exactly this particular dependence of this k-squared here. This is not an equation of motion. This is a null test. So if you measure at a large number of k, this particular combination of variables, these alphas are to do with the Lagrangian, but they're in principle irrelevant. If you measure at more than 8 different scales of k, if you can at any one redshift, if you cannot fit your data to this sort of equation, then you just cannot explain your data in a single scalar field. This is, of course, a lot. This is very general. But if you look at, say, some subclass like f of r, you get some equation like this, but with only one parameter, which happens to be mass of the scalar field at that point. OK, so we're out of time. So I'll just the point I'll make is that really the important thing is that you want to be testing for scale dependence, because that is the thing that tells you whether you have something like a Lorentz invariant theory or some brain or something like this. And this scale dependence is the only thing that is determined by the properties of the dark energy itself. So of course this is very tough, but the question is, we've not really been thinking about scale dependence in terms of doing tests. So is there some way of more optimally doing such measurements by concentrating on a single redshift rather than doing something like Euclid or W1st, which does many redshifts at the same time? Thank you.
Have you looked at the effects on Big Bang nucleosynthesis?
You mean of these scalar theories? So no. So in principle, all of them have certain ranges of, the issue is the problem is the following: that you have no real grounds for picking any particular functions here. So you can always construct something that might be interesting at late times and yet evades the universe. But yeah, so in principle, they change the value of G compared to what you see today, and therefore there's some constraint. But there's a value of G for the background, there's a value of G for perturbations, and the two are different things, in fact.
What kind of measurement would be the best to distinguish between the different kinds of models?
No, so you see my argument is that first you should just find that lambda CDM doesn't work. If you've done that, then you have there's one simple variable you can test, which is this eta, which I was just talking about, this anisotropic stress. That tells you a lot, because basically, if you don't see it, you've completely killed this class of operators here. So then you're left with just these two. And then everything, if you do see it, then this thing is definitely there and it's important. So I think measuring this eta, it's a completely model-independent measurement. This is the very important point. You don't have to evolve start from some sort of initial conditions, evolve them forward. You just take a slice, and you just take a slice in redshift space, and you perform a measurement there, and you can find whether you have eta or not. Now, the next thing, which requires a lot more, and you can do this with Euclid in principle to something like 10% accuracy if you assume eta is constant. The question is what you do afterwards if you find out it's, for example, there. And that means doing the scale-dependent measurements, which of course require a lot more accuracy. And to be honest, I have no idea if that's really ever will be feasible. But I think that is the thing that's going to actually allow you to distinguish between different even frameworks. Do I have Lorentz invariance or not? Am I dealing with something that's a scalar field, or am I doing something completely different? That will require a measurement in k-space.
Let's thank you.